as being something more than what we typically see in a single core memory machine when we actually have data that's replicated. And so the question was, well, okay, what does it mean for a process that's running on some node in some far off land when it witnesses a piece of data? How relevant is that data, given that there could be other instances of the data floating around? And so we came up with a bunch of alternatives. We settled on the weakest one, the one that provided the fewest guarantees because it seemed to be the most flexible, the most malleable. And then we observed that there's all sorts of things that can go wrong, right? So that was where we left things yesterday. So what I'd like to do today is try to formalize this a little bit more, right? Sort of put this on a more formal footing. So we'll talk about semantics that can be used to sort of explain what eventual consistency actually means. And then we'll try to come up with, we'll explore a bunch of ways that we can remediate some of the problems, right? And the way we're going to do this is algorithmically. We're going to look at different kinds of algorithmic structures that we might be able to use to sort of control and harness the power of eventual consistency in positive ways. And then we'll also look at language abstractions, ways that we can actually really bring PL concepts to bear and use the power of things like SMT and all other fancy tools, static analysis and things like that, to actually tell us whether our programs are doing what we expect them to do in this sort of universe. Right, okay. So we'll dive down into a little bit of math, as it were, but it's still early in the morning, so hopefully it's not too bad. Right, okay. So what is our model? Our model is we have a collection of replicas, and there's going to be a collection of computations that are going that's going to find its way into one of these replicas. We're going to sort of capture things, right? We've got clients, and we're going to call these clients sessions, right? And we're going to order the set of statements that exist in the session. So think of client 1 executing statement 1, then statement 2, then statement 3. So we've got something called a session ID, and within each session, there's a tag that indicates what instruction we're running on, things like that. And we've got a bunch of replicas, right? So S, I, and R are just sort of the indices into this universe of clients and replicas. Remember that last time we said the way we're going to model execution here is by this notion of an effect. So an effect is just an operation, as it were, that a client issues, along with the value that finally gets generated when it executes that operation on a particular replica. So in our world, an effect is going to be the session that this particular operation came from. Operation, right? And we're going to leave this open, but think of these as reads and writes and things like that. And the value that actually got generated when you ran this particular operation on some replica. Now, because this world is very, very unconstrained, all of these things are just going to live in this soup, right? There's just going to be a bunch of these effects that are floating around. And what we're going to try to do is move these effects from one replica to another non-deterministically. And we're going to try to make sense of what that sort of non-deterministic movement actually means in practice. The other thing that we mentioned last time was that we have these relations, right? These operations that we execute don't execute completely independently of one another, right? So, for example, if I'm a client running in a session that's executing a session where I execute operation 1 and then operation 2 is related to operation 1 because they happen to be in the same session, and operation 2 follows operation 1. So we have a relation called session order that captures that, SO. When I have an operation that finds its way, or an effect that finds its way onto a replica, that replica has a bunch of other operations that it's executed. Those operations are visible to this operation. So when I'm trying to do a read, and I find myself on a replica that has done a write to that same variable, well, that write becomes visible to this read. So we have a visibility relation. And we have one other relation called same object, because it is relevant for us, as we'll see, to know to distinguish between the fact that I'm writing to X or the fact that I'm writing to Y or reading from Y. So we're going to sort of just distinguish the set of objects that we have in our world. Okay, so that's sort of a little bit of setup on relations and effects. So what is the state? So an execution state is just a bunch of these effects along with these relations, right? That defines how these effects relate to one another. Okay, so that's the sort of computation side of the world, right? But then we also have the data side of the universe, right? So, and that's represented by the store. So a store is essentially a map from a replica to a set of effects. So every replica manages a collection of these effects, and that's what data is going to represent. And my entire state, the state of the world, is going to be represented by the relations that we've built up and these effects, E, the store, theta, that has all of these effects attached with replicas, and the actual computations themselves in these different sessions, sigma, right? So what we're going to do is now sort of try to understand exactly how we can move from one state configuration to another state configuration. Okay. Now there's this thing called consistency class that I haven't defined yet, but intuitively think of a consistency class as a kind of constraint. So if I assert that a particular operation must be strongly consistent, for example, then that imposes certain constraints on both the execution state, what can be visible, what needs to be visible, what needs to be in session order, as well as the store, what effects must be available in the store in order for this particular operation to take place, right? So tau is essentially nomenclature for constraints. Okay. So bear with me just for a little bit. You know, there's a little bit of Greek here, but it'll go away quickly. So the first thing, and we don't need to go through all of the, well, maybe I'll just sort of highlight. Right. So the first thing we're going to do is we're going to have this little relation, this auxiliary relation, hook arrow, that's going to tell me what it means for a replica to do something meaningful, right? So if I have a replica, R, and inside this replica, there is some effect, right, eta, which is defined by this quadruple that represents a session and an index and an operation and so on. And I execute this operation in the context of this replica, looking at all the stuff that the replica, all the effects that the replica provides, right? That's defined by this curly, this squiggly arrow to produce a value v, right? I now have in my hands an effect, a bona fide effect. That is, I had some operation coming from some session. I ran this operation on this replica, and I get a value v, right? So that's v. And now what I'm going to do is I'm going to essentially say, well, okay, if I can do that, there are a couple of things that I need to also keep around, right? If I can produce a value v on this replica, I must also keep around the fact that this replica executed in the context of some session. That is, it has a bunch of dependencies that it used or that was available to it. That's defined by SO prime. So for example, if I'm the third statement in a particular session and I execute this operation, well, I want to keep around the fact that, okay, I was the third statement in this session. And so SO prime defines a relation over all of the other operations that this particular effect was dependent on within a given session. Similarly, I'm sitting inside of a replica when I evaluated this operation, and this replica has a bunch of other effects associated with it, right? Those effects are visible to this operation when it's running. And so we record that as well as vis prime. So vis prime and SO prime define the dependencies that this particular effect relied on as it performed its operation. Now observe that in this particular judgment, we're not changing the store at all. I'm not doing anything with the store. I'm just telling you what it means for a particular effect to run on some particular replica and what the relations, what kind of relations are dependent, what other effects this particular operation was dependent on. Okay. So we've got a log, we run some operation, and then we sort of augment our relations based on the replica that we were executing. So nothing interesting to the store here. Okay. the interesting things happen. Two interesting, so that particular judgment sort of simply does the setup, right? We're not doing anything, we haven't done anything interesting yet. So there's going to be two classes of operations that we're going to consider. The first class is a transformation on the store itself, right? So effect_vis does the following. It says, if you have an effect, right? If you claim you have an effect that's sitting in this soup, right, that we generated from the previous rule, then I can incorporate that effect into my store. Recall that my store was a mapping from replicas to lists of effects. I can incorporate that effect into my store if the following conditions hold. So the things on above the line represents the conditions that must hold. So if I'm running on a replica R, right, I can add this effect to R in theta if I know inside R all of the dependencies that replica required with respect to visibility and session order were available, right? So recall our previous example. I have an operation that we talked about last time. I have an operation, say, get balance on a bank account. And I run this operation on some replica, right? And in that replica, I found that the bank account actually had $100 in it because there was a deposit. Now, I'm going to copy this operation, right, this effect, onto some other replica, right? But in order for me to make sure that when I execute this operation on this other replica, in order to make sure that it makes sense, surely I should make sure that I have that particular $100 available here, right? That would be something that we might want to expect. The store can guarantee this, right? Can guarantee this kind of constraint without compromising availability by simply not publishing this effect until all of the dependencies are actually available. This particular property is known as causal visibility. So again, if I'm the store and I get an effect, since I know what the relations are on visibility and session order, I can simply wait on that replica. That replica can wait before it actually incorporates this operation until it gets the data, until it gets the visibility and session order dependencies propagated to it. Observe that just because that replica waits doesn't mean that other replicas can't continue to work, right? And in particular, the client is not blocked because the client has just sort of issued the operation and it's waiting for the store to do what it wants. There's nothing that prevents the client from not continuing to perform its activities. So causal visibility is a store level property that essentially provides stronger guarantees than what you would have gotten if you didn't consider any kind of visibility, any kind of session order guarantees, but is still, surprisingly enough, coordination free, still highly available, right? Because the store manages this. So observe that in this particular world, we haven't changed the execution state. The judgment keeps the execution state just the way it was. That means that this has nothing to do with the client. The client is sitting somewhere here. It doesn't know anything at all about what the store is doing. The store is sort of mucking around, propagating effects from replica to replica, waiting for certain conditions to hold before it publishes that effect on that replica. Let's look at EC in contrast. The EC rule has a constraint on it. The constraint says, I have an operation, and I want to execute this operation as an eventually consistent thing, right? As something that's eventually consistent. What does this mean? Well, I'm allowed to transition to a new state, to a new configuration, where I've consumed this operation, right? Provided that I'm allowed to, I can go to a replica and have this operation be recorded within that replica state. Okay? So observe that theta, the store, hasn't changed here, right? So from the perspective of the client, he issues an EC request. So his goal is, the client says, I have no constraints on what the store needs to be. I can go to any replica. I can just push this operation onto that replica. Whether that replica chooses to execute the effect and when it chooses to execute the effect is based on this other property up there, But it doesn't stop me from doing anything. I don't make any constraints on what the data happens, what configuration that replica happens to have. So if this particular rule means that a client who executes an operation under eventual consistency can do so with no constraints on the structure of the store or the structure of the replicas that he's operating under. Does that make sense? So we have two perspectives here, right? The perspective of the world from the context of the data store, which looks at what's found in replicas and what effects exist, and the perspective of the universe from the view of the client, which says I expect certain constraints on the store before I'm going to allow this operation to continue. And in eventual consistency, that there are no constraints. So any operation can go to any replica, and as long as we set up the visibility and session order relations using hook arrow. Okay. Here are two other examples of constraints that we might want to generate from a client. The first constraint is called causal consistency, right? Which is a little bit different than the causal visibility rule that we described before. So suppose that I have a client that's executing operations O1 and O2, right? This client might say, you, the store, are not allowed to do anything with O2 until you've actually seen O1, right? That is, I won't allow you to make any kind of change to your state until O1 is available on this particular replica, right? So if I have a causally consistent operation, I'm allowed to take a step. That is, I'm allowed to go to a new configuration, provided that the replica that I target this operation on includes all of the session order dependencies that existed in the client. That's that SO inverse operation that we have on the antecedent. So observe what this means. If I'm a client and I can go to any replica, R is free in this rule, it means that every replica, any particular replica that I go to, must have all of the causally preceding operations on it available to it before I'm allowed to execute this operation. So in this context, is causal consistency a highly available consistency class or not? No, it's not, right? It means that if there was a network partition, right, and I constrain my operation to be causally consistent, I will block, because I expect that any replica that I can go to must have all of its preceding operations. So the distinction between causal visibility and causal consistency is very, very profound. Causal visibility is a property that is managed entirely by the store, that doesn't involve the client, that dictates when the store is allowed to do something interesting. Causal consistency is a property associated with the client that blocks a client action from taking place until certain conditions exist in the store. And the last operation is something which is strongly consistent, right? So what does strong consistency say? It says, if you have an operation that you claim is strongly consistent, you can move to a new configuration, right? Provided that for every replica that exists, for all the replicas that we have in our system, we are allowed to have all of the effects that are necessary, all of the effects that I need in order to run exists on all of these replicas, right? So we're saying that everybody every replica has all of the dependencies that are necessary in order for me to apply this operation. So, in other words, we have complete global consistency on every single action. So this is a much stronger constraint than causal consistency, right? It obligates that every operation that I'm going to perform in E, right, in my configuration, is in fact available on every single replica. So with these three classes of consistency levels, we can now ask various questions. For example, how do we enforce this level of consistency? How do we enforce causal consistency at an implementation level? How do we express properties of programs that relate to one of these consistency levels? Are there different consistency levels besides these three? And so forth and so on. Okay. So what I'd like to do, assuming that the sort of rules sort of give you an idea of exactly how we're sort of envisioning this universe, this sort of system, as long as that's clear, what I'd like to do next is sort of go through a number of instantiations of different techniques that we might apply that allow us to sort of manipulate these kinds of principles. So are the rules generally clear? Do people get the way we're thinking about the world? Yes? Okay. Right. Okay. So broadly speaking, there's three ways that we can think about manipulating these kinds of systems, and I classify them. I classify them crudely in sort of one of three buckets. One is sort of algorithmic based. That is, we're going to just define algorithms that will guarantee not to screw up, regardless of regardless of the consistency level that we're using. So we're going to fix our constraints to be EC. That is, we're going to admit the weakest possible set of behaviors that we can, and we're going to impose properties on the algorithms and data structures that we write that guarantee that no matter what we do, no matter what kind of ordering or non-determinism exists in the way data is replicated and propagated, that we'll still get the behavior that we want. And this broadly falls under this category of structure called CRDTs. These are commutative and convergent data types, right, that are cognizant of the fact that they may be replicated. And what we'll see, hopefully, is that it can be done, but it's not easy, but we can do it, and we can build a library of these things. That's the first thing. There's another approach which says we're going to define programming models, right? Rather than defining things in terms of algorithms, as it were, or just data structures, we're going to define a programming model where the model itself sort of defines constraints on what you can write and what you can't write. Okay? So we're going to change the way we think about computation, not just the way we think about data types. We're going to change the way we think about computation. There are a bunch of proposals that have been made around this. One of them, LASP, is in fact designed by Christopher here, and so I would encourage you to sort of talk to him afterwards if you have questions about that. And I won't presume to do a better job than he can on talking about that, so I'll talk about something else. And then the last approach, which is what we've been working on for the last few years, is what I refer to as semantics-based. That is, rather than just defining a programming model, we're going to essentially try to relate the operational semantics that I talked about on the previous page and instantiate that directly inside of a programming language, right? So we're going to have our programming language be fully aware of notions of consistency at various points. We're not going to make any constraints at all, but instead, we're going to provide checkers, as it were, that enforce the kinds of properties that the programmer expected. And so I'll focus the bulk of the talk on some of those ideas. Okay, so before I go into that, let me spend a little bit of time introducing you to the idea of CRDTs. So the techniques that I'm going to talk about are from a paper by Burkhardt and his colleagues that was published in POPL in 2014. So if you're interested in more details about that. So here's our here's the starting point for what we're going to do. We're going to think of data as being defined in terms of a data type. So an object is going to have a collection of methods applied to it, and we're going to assume that these objects can be freely replicated, right? And when they're replicated, a method invocation can go to any replica and get the data that it wants. Okay. So there are a couple of things that we're going to enrich these objects with. First, we're going to enrich them with timestamps. So we'll assume somehow that we can timestamp every particular object as it gets created. And we're going to use these timestamps in certain ways. When we send a message, right, the thing that we actually send is under the control of the data type implementation. So as we talked about before, we might send an operation, right? We might send the operation add or multiply or get balance, things like that. Or we might send states. We might apply a series of operations on a data type, on a particular replica, and send the resulting state from one replica to another, right? So there's flexibility in the way we envision how we do things. But the guarantee that we're making, the guarantee that this particular formalization is going to give us, is that regardless of the order in which messages are communicated from one replica to another, eventually, all replicas will see the exact same structure, the same state, the same value of that object, right? So that's the guarantee that we must enforce. Now, as you can imagine, I can't take any data type and trivially turn it into a CRDT, because surely there's order that matters in the kinds of data types that we write. So if we find ourselves wanting to use CRDTs, we have to think very, very carefully about things like order and commutativity and convergence, all of the things that exist in its acronym. Right? So in Burckhardt's formalization, a replicated data type has a bunch of things in it, but there's sort of three operations in addition to the operations that actually exist in the data type itself that are relevant. The first is an operation that actually performs some computation, do, right? So it says, give me an operation, give me some state, and I'm going to execute this operation and give you a new state, okay? And then there's two sort of implicit or hidden operations that are hidden from the data type itself, called send and receive. And send and receive is our methods that are executed implicitly by the system, right, non-deterministically, that takes information from one replica and propagates it to another. Okay, so send takes a configuration on some replica and sends a message to another replica. Receive takes a message from some replica and applies it to the state that it has. Okay, and this can be done in completely non-deterministic ways. Okay, so with that, we can now write specifications for what we mean when we have a replicated data type. So here are two particular instantiations. And as you can tell, these are counters, right? So, but they don't look like counters, right? The specification doesn't look like a counter, which should give you pause for how complicated things can get, right? So let's go through them. So here are two particular instantiations of a counter. So the first is what we call as an op-based representation. That is, the notion of a state that I'm going to keep is essentially an operation, add, for example, right? So that's what a counter does. It adds something to some existing value. So I have two methods on a counter, read and increment. And observe that the notion of what a counter state is not just an integer, right? In fact, it's a pair of integers, right? N cross n. And the reason is, imagine that I go to a replica and I increment its counter value. I give it 2. I increment it by 1 and then I increment it again. It was initially 0, now it has 2. Okay. So now I send this value 2 to some other replica. It says, yeah, okay, I have 2. Right? And then I increment it again. Right? I increment it and it becomes 3. But instead of going to this replica, instead of sending the message to this replica, I send it to some other guy who gets 3. Right? And then it falls down to this third replica. Now, this replica may be a bit confused. Should it add 3 because there were 3 new increments, or should it add 1 because it already saw 2 before? How do we know, right? There's no information if we just kept a single value to tell the distinction between new things that have been added, or things that were already seen before from some other path that are being repeated, right? So the pair of values here represents a counter value, A, and the last time I did a send, right? I'm going to record how many times I incremented the counter locally before I did a send, and that's going to be D. So for example, when we increment a counter, we're going to increment the local value, A, by 1, and we're also going to increment the number of times I've incremented the counter since I last did a send, right? So that becomes D plus 1 as well. When I do a send, I'm going to send the value A, right? And I'm going to reinitialize. I'm going to initialize the count D because I've now sent the value, right? When I receive a counter object, right, I'm going to add to my state, right, whatever my state was, A, the value of D, because that represents the number of increments that have happened locally by this replica since the last time I saw it, right? They're very persistent. Okay. So I encourage you to sort of just work this out on paper, right? But it makes sense intuitively, right? I need to keep around history when I have a counter value. I can't simply just assume that the existing state of the counter is what the actual state of the counter is, because it can come to me from a number of different paths, and I don't have any control over what those paths are. There's another way of thinking about counters, right? Instead of just thinking of the operation itself, what I can do is say, why don't I record the value of a counter that every replica thinks it has, right? So instead of thinking of a counter as a single value, let me think of a counter as a vector indexed by the replicas themselves, okay? So when I increment a counter, what I'm going to do is say, well, if I'm on replica R, I'm going to increment the counter value on R, right? And when I send something, I'm going to actually send that entire vector, right? When I receive a counter, when I receive a message, and I'm on replica R, I'm going to look at the index that I got for R in that message, and if that index is smaller than my value, then it means that that particular replica that sent me its notion, that its belief of what my counter value was, it was out of date. I've already done stuff since it last communicated with me. So I'm going to ignore it. I'm going to take my value. On the other hand, if that counter, if the notion of the counter value for that replica for R is greater than what I have, it means that guy has actually done interesting things, right? And I haven't seen it yet, and so I'm going to incorporate it. Hmm? Yeah, it's like a vector clock. It's sort of like a vector clock, except that it's not indexed by any particular operation, right? But yeah, it's just like a vector clock, right? Every process is going to record information about itself, right? So when I do a read, all I'm going to do is sum up the values of all the counters that I've seen thus far, okay? Does that make sense, right? So we can either keep vectors and sort of index each replica value, each counter value per replica, or we can sort of keep differences of counter values and sort of have epochs between sends and just sort of incorporate aggregation or counting on that level. Both of these, So both of these operations for something as simple as counter requires a little bit of thought. There's another kind of, but neither of them required any use of timestamps or anything like that. So in distributed systems, it's often the case that we resolve conflicts, we resolve things where we're unable to come up with a consistent view of the world by some kind of arbitrary mediation, arbitration. A timestamp is an example of that, right? So a well-known data structure in these kinds of distributed systems is a last writer wins register. So think of a register as holding a value, and all replicas can sort of manipulate this value in different ways. What happens if two replicas provide a value for this register that are inconsistent with one another, that aren't related in any meaningful way? So what we're going to do is simply use a timestamp. How we get this timestamp, I'm going to leave abstract for now, and we'll get back to that in a little bit. But in this particular diagram, we've got a register X that's replicated on three particular replicas, and the first component is the value, and the second component is the timestamp. And so this diagram sort of shows what can happen as you sort of go, as the execution proceeds. So for example, replica X2 stores the value 2 into the register, it's got timestamp 1. Replica X1 stores the value 1 at timestamp 3, and so forth and so on. And when they communicate with each other, they'll use the timestamp to sort of figure out which guy wins. Okay. This doesn't seem that simple, because I don't have any idea of how we actually maintain these timestamps, right? So now we've got two examples. We've got counters that took me about 10 minutes to explain, which seems really, really long, 10 minutes too long. And we've got timestamps, which I can't give you any real simple explanation for how they work. So, and that's just for things that are really, really simple, right? Register and a counter. In fact, the world is significantly more complicated, right? So suppose that instead of a simple increment counter, I actually want to incorporate multiplication, right? I want to have a counter against which I can multiply as well as add, right? If you sort of think a little bit about how this might work, you'll quickly see that it doesn't naturally translate to the same formalization that we had before. And that's because multiplication is not commutative with addition, right? So 2 plus 3 times 4 is not the same thing as 2 times 3 plus 4, right? So we can't just sort of swap operations in arbitrary ways. So if I want to, for example, have a counter that actually incorporates multiplication, I'm going to have to turn multiplication into addition, right? And get back into the world where I can actually think about commutativity, right? So I might define multiplication as something that simply adds the thing that I'm multiplying by. I wrote that wrong, but as an addition operation, right? Repeated successive addition. So for simple things like counters and registers, we're already sort of pushing the limits of thinking about how easy it is to write. What happens when we have more sophisticated data structures, right? How can we actually think about eventual consistency or the meaning of data structures that are more sophisticated than simple single value entities and still get them to work regardless of how we implement replicas? So the particular example that I'm going to use is a set, right? So imagine that I want to build a set that has 2 operations on it, or 3 operations on it. I can add elements to the set, I can remove elements from the set, and I can query the set of elements in the set. Right? So the question that we want to ask is, how do we know that if I have such a set that gets replicated on many, many different nodes, that all of these nodes will in fact ultimately have the same contents? And the reason why this should give you pause is because what happens when I do a remove, right? If all I'm doing is adding elements to a set, you could imagine that eventually everybody will get everything. But I have removes, which means that periodically some replica says, get rid of the element 3, right? Now, there's no time order, there's no global time, right? We don't, the fundamental problem we've run into in this universe is that we don't have a notion of global time. So how do I know when this remove happened with respect to all of the other replicas that are doing their own adds and removes, right? We need to somehow figure out a way of coordinating among or remediating the tension between the addition of a value and the removal of a value when we don't have a single time order, single timeline to do that. So the sort of classical way of doing it, the most obvious way of doing it, is inspired again by the way we implemented counters, right? Where we had a vector for every replica. And here we're going to do something similar to that. What we're going to do is we're going to record the set of things that I've added to the set, and I'm also going to record the set of things that I removed from the set without actually doing the removal, right? We're just going to record that information. So, I'm sorry? Yeah, right, exactly. So, and we're going to there's going to be this UID that we're going to keep around that's going to make sure that we sort of keep things separate, that we know who's doing the addition, who's doing the removal, so we don't get confused by looking at the same thing twice. So when we want to add something to a counter, to a set, we're just going to add that element we're going to add my ID, right? It says that I'm the guy that's doing the addition with this particular value to the A part, to the A component, right? And when I want to do a remove, I'm going to do the same thing, except I'm going to add it to the R component, right? And when I do a query, I'm going to remove all of the elements in the R component and then see what's left and in the A component, and that's what I'm going to return. Right? So you could sort of vaguely see that what we're trying to do here is just not stomp on the set itself, right? We're going to treat things very, very functionally, right? Not actually do any kind of removal, and we're going to compute the final thing based on what the A and R elements are, right? So that's one way of doing it, but observe that this is not particularly efficient, right? We need to now keep around for every remove operation, we're actually recording that inside of this other data structure, right? There's that union operation on remove that we have to keep around. And we have to do the same thing for every add operation. So there's not a whole, so this can grow very, very large. So in practice, or if we wanted to actually make things more efficient, we need something substantially more complicated, right? And I'm not going to go through all of the details here, but I think it is worthwhile to sort of pause and take a look at the complexities that something as simple as a set, as incorporating a set has in a distributed system, right? So without going into the details, here's the intuition. The intuition is that I'm going to record, I'm going to keep around 2 bits of information. I'm going to keep around information about the elements in the set that are active, that I don't believe have been removed, and information about the total number of operations that I've actually performed. So rather than actually recording removes, I'm going to embed information about removes inside of an integer, right? So if I know the set of active elements that I've got, and I know the total set of operations that I performed, we can play games, right? To sort of use arithmetic to try to figure out exactly what elements actually exist. So rather than going through the code here, let's work through an example to sort of intuitively see how this might work. So I want to build a set, and I've got 3 replicas, right? So here's the way that I'm going to build one of these sets. So suppose that I want to add 13 to the set, right? So I'm going to record in this data structure that we built on the previous slide 2 bits of information. I'm going to record the fact that replica R1 added 13, right? And its active count is 1. It thinks that there's 1 element in the set, right? And that as far as R1 knows, that's the only thing that's happened. There's no other, it has no knowledge about any other replica. It's done 1 operation, so it's got that one thing in it. Okay. R2 will do something similar, right? So it adds 15 to the set. As far as it knows, nobody else has manipulated 15, right? Nobody else has added 15, so it's got one instance of 15 that's active, and it's performed one operation. So R2 is also 1. Now, non-deterministically, underneath the covers, R1 can send a message to R3 publishing its particular value, right? What it believes the set happens to be. So here, R3 receives this value, and it says, oh, okay, as far as I know, based on what R1 has told me, the set has one element in it that R1 was responsible for, that has 13. And as far as R1 knows, there's only one element in the set. Okay. I can also propagate that information to R2. And R2 merges this with its state, right? So now R2 believes that there are two things in the set, 13 and 15, one contributed by R1, one contributed by R2. Okay. Now, so far there haven't been removes. So let's see what happens when we start doing more fancy things. So I'll add another element to the set. So R1 can add 13 again, right? But there's still only one value of 13, but we'll record the fact that I tried to add 13 once more, right? There's two things that I've done, but I only have one. But if I do a remove, everything gets cleared out, right? And I can propagate that to R3. R3 is happy. Oops. What happens when I do a remove now? So when I do a remove, right, in R1, it clears out its value of 13, right? So it says, I don't believe that 13 exists anymore because I've done a remove. But by the way, I've done two operations. You should be aware because I've communicated this information to other guys. So they need to know that that I need to record that information. So I've done two operations, but I've cleared out remove. Now, I can propagate that information to R2, right? So R2 gets this information, and it says the following. It says, as far as I knew before, R1 had only performed one operation, right? And that operation was 13, right? Was an add of 13. But I'm getting a message from R1 now that says it's performed two operations, which means that it's ahead of me in terms of the things that it's done since the last time I saw it. And therefore, I'm going to believe that the state that it believes it has is, in fact, an updated state. So it will then go ahead and clear out R1, simply because it got R1 gets 2 as part of the sort of total count. R2 can also talk to R3, right? So R2 is going to talk to R3 with its notion of what the world is, right? And observe that there's this sort of line that's crisscrossing. This should sort of give us pause. R1 has communicated to R3 with some value. R2 has communicates to R3 with some value. The value that R1 communicated, though, was later than the value of R1 that R2 is communicating to R3. Observe that R2 got some view of the world from R1, but that happened before the communication of R1 to R3. Okay. So we've got to sort of play some games here, right? And the net result of this is that R3 better accept R1's value, not the value from R2. So the value that R3 thinks the register that R1 has for 13 is in fact 2, because it hasn't seen the remove yet. This is taking me a really, really long time to explain, which means that there's something very, broken here. But anyway. And so we can go on, right? And we can sort of propagate this information back and forth. This is the state of the art of CRDTs. Yep. We assume there's causality, right? There's client level causality. So the client can't do a remove without having done an add before. But where that remove gets witnessed, which replica that remove actually gets seen on, can be different, right?
So the client could then
add, remove, right? It can't do a remove without having done an add. Yeah, but all I'm observing is that the store can see things in varying orders, right? No, 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 no. That would add even further complication. So anyway, so what we've done here, what we've constructed is a very, very sophisticated. Oh yes. So because you only need to record, because the information that we've done to remove is available in the fact that we've got a 0 in that slot. So we've already, there's enough information there, if I have a 0, to indicate that I've done the remove. So I can just take the difference between, I can use that information in the actual definition. So I don't need to record, so I only need to increment the map on adds, leveraging the fact that when I do a remove, I'm going to have a 0 in that slot. So when I communicate that information, you can use that, you can build that information. In fact, you can see that in the receive slide where it looks at VAS equals 0, right? So it takes advantage of that in the way that it builds its structure. Right. So CRDTs are a very, very powerful mechanism that allows us to think about complicated data, that allows us to think about data structures, but at a significant price in conceptual elegance and simplicity, right? So this is not the way that I would write a set, but I need, but I need to now think about things in that way. So with that in mind, right, are there alternatives? Are there things other than CRDTs that we can use that would allow us to still effectively program over these kinds of systems? So I'm going to talk about two things. The first is a programming model that says, forget about eventual consistency. It's just too hard to reason about. Let's write down our programs in a way that is more sensible for the average programmer, right? Because if we have to expect the average programmer to program these kinds of data structures, it's simply not going to work. And then the alternative is say, well, we'll give programmers a little bit of credit. We'll give developers a little bit of credit, but we'll try our best to prevent them from shooting themselves in the foot, right? So we're going to provide other infrastructure that would make it harder for them to screw up. Okay, so these are sort of two different perspectives on the world. So the first perspective is an idea that Burkhardt came up with a couple of years ago called cloud types. So here's the intuition. The idea is that we've got replicas, but in some sense, these replicas are trying, even though they're not always successful, they are trying to sort of play nice with one another, right? Their goal is to sort of eventually come back with a consistent value. So one way of sort of realizing this is, rather than thinking of all replicas as being equal, right, why don't we say that, well, some replicas are more equal than others, and we're going to allow them to sort of mediate the actual values that we need, right? So the intuition is that I have a replica that's sitting on a server, right? So let me think of a server as a replica, and let me think of a client as another kind of replica, and the client has local state that it manipulates. The server has its own state that it manipulates, and clients are going to talk to the server periodically, just as in a cloud environment. And what we're going to do is we're going to always look at the client, at the server, as the harbinger of truth, right? If there's ever any sort of conflict, the server gets to win, right? Now this sort of isn't EC anymore, right? But it's a model that sort of gives us some of the benefits of georeplication. We still have replication, but with the constraint that we're no longer going to think of everybody as an equally likely target for data that we want. I'm sorry? Very good question, right? Once you do that, all sorts of things happen. Bad things happen. You don't want to go there, right? So no, right? But as long as you're willing to sort of live in this world, you can actually write down somewhat interesting program. So here's a really simple program. I've got a program that's implementing a shopping cart, right? And what I want to do is I can do things like buying. I can record my intention to buy something, and then having bought something, I can record the fact that I bought it, and then ultimately I display all the things that I bought. Okay. So the code in and of itself is not particularly interesting, except for two things. One is that we distinguish between those objects that we want to have replicated. So we'll be very clear about the things that we want to replicate. In this particular case, there's this integer called the to buy, which represents the set of the number of things that I want to buy. Right. I'm sorry. Yeah, it's an ID of the things that I want to buy. And I can perform local computation. That's not particularly interesting. The really interesting thing is this one particular operation called yield. So what yield does is it says, I have local computation that I've computed. I'm going to now propagate this information, just like the send operation occurred in a CRDT formulation. I'm going to propagate this information to a replica, to the server, right? And the server gets to now figure out how to merge this with its particular state. But yield, I want yield to be available. That is, I want it to return right away, right? So that's the trick. If I actually had to wait for an RPC, then I haven't done anything interesting. So the question is, how can we allow yield to be very, very fast? That is, I perform the operation in the background and still continuing on with my own computation without sort of breaking interesting properties. And the way that they formulate this is through an abstraction called a revision diagram. So think of a revision diagram as a graph, right, where nodes in the graph represent communication points, right, and edges in the graph represent control that reverts from one replica to another, or from one server to a client and back. So for example, on the left-hand side of this picture, a client a server, right, or some operation might set a value of x to be 1. Okay. Before it did that, though, it might have gone off. It may have propagated the value, the object x, to some local guy, who happens to set x to 5, right? Having set x to 5 locally, it might choose to do a yield, which propagates x back to the mainline branch. So think of this as Git, except for data types in a very constrained way. And when the mainline branch chooses to see the value, it sees 5. That's the first idea, right? And the second and third are sort of similar variants on this theme, right? So we have branches, which represent the propagation of information from server to client, and we have joins, which are like commits, from clients back to servers. Except that rather than doing it on files and text, we're actually going to do this on data types, right, in a very, very constrained way. So here's a little picture of the example that we had before, and it's worth sort of going through this just a little bit to see exactly what we can do. So I have two clients, device 1 and device 2, and device 1 issues a command to buy eggs, to buy 6 eggs, right? And the server, at the same time, allowed device 2 to run, which said, I want to buy 2 eggs, right? Having bought 2 eggs, or having indicated its intention to buy 2 eggs, that client, device 2, yields. What does yield do? Yield propagates the intent to buy 2 eggs back to the server, right? And the server continues. Right? Device 1 has an intention to buy 6 eggs, right? And that information gets propagated to the server as well, right? And so forth and so on. And so you find all these yields and operations taking place. And each branch represents an asynchronous invocation. So when device 2 does a yield, it doesn't stop. It sends that information, and it's allowed to continue to, for example, buy 1 unit of oil, and so forth and so on. At the end of the day, we see, if I do a display, I have the intention to buy 8 eggs, 1 oil, and so forth and so on. observe that the order in which I perform yields and the order in which I sort of propagate information from the client to the server can change the results that we have in our program. So on the right-hand side, we have a similar kind of revision diagram with some subtle differences that lead to a display of 2 eggs rather than 8 eggs. And the reason is that when I indicated my intention to buy 2 eggs, right, I go back to the server. The server records the fact that I bought 2 eggs, or that I intend to buy 2 eggs. It also records the fact that device 1 indicated it's interested to buy 6 eggs, right, which is 8 eggs. But whereas before, the bought egg 6 operation on the left, the yield operation that followed it didn't actually communicate to the server. Maybe the server was down, and it never took place. On the right-hand side, the yield operation after purchasing 6 eggs was in fact communicated to the server. So we decremented 8 minus 6 to get 2. So yield is a non-deterministic action which has the flexibility to actually communicate with the server when it wishes or not. So this is one way that it differs from, say, a git commit. So it's like a git commit where the commit may choose not to commit at all. Okay, good luck. Right. So this particular model gives us a way of programming with replicas without the complexity, conceptual complexity of CRDTs, but it has some downsides, some serious downsides. The most important of which is that it's not fully decentralized. If that server goes away, we will get into behavior like the one on the left, where we actually don't see the results that we're interested in. Okay, so I've gone over 2 ideas here. One, let's look at ways of tackling the notion of replication head-on in the data types themselves. Yuck. Let's look at ways of constraining the way we program so that we can elide some of this complexity by simply choosing to see certain values and not necessarily have the kind of convergence that we want, okay, but at a loss of expressive power. The third thing that I'm going to talk about in the remaining time that I have is a way where we will try to have our cake and eat it too. We don't want to lose the power of georeplication. We want to get all the benefits that provides to us, but we don't want to be stuck thinking about algorithmic details, low-level algorithmic details, the way we did with CRDTs. So here's the idea. Ultimately, the challenge that we've got so far, that we've witnessed, is as a programmer, I'm not interested in the particular nuances of how an observe remove set should work. I just want to build a set. And I have some invariants that talk about sets. And I would like those invariants to be translated into actions on the underlying system without having to actually program what those actions are. So our goal is going to be to try to see if we can't come up with a way of doing that. So the programmer has some ideas in his or her head about what they would like their system to do, their application to do. I want my account balances to be non-negative no matter what happens. I want my usernames to always be unique if I'm building a Twitter application. If I'm building an auction system, I don't want to allow bids to happen after the auction is closed, things like that. On the other hand, the data types that we manipulate in our system don't know anything at all about any of that. They only know about things like consistency and isolation and serializability, things that have that are far removed from these higher level invariants. Right? So we've got stores on the bottom, right, which is what we've been talking about. We've got a whole bunch of ways to muck around with these stores. I've only talked about a few of them, like eventual consistency and causal consistency and strong consistency. And all of these things have these very, very different trade-offs, performance trade-offs, right? And we don't know necessarily where these trade-offs are going to go. What we want to do is to somehow figure out a way of determining which arrows we want. What is the trade-off between performance and communication and all that? That satisfies higher the invariance that the programmer actually wants. So if the programmer is interested in making sure that bank account balances are never less than 0, can you turn that into an implementation that guarantees that based on one of these sort of consistency levels, right? The claim here is that now we've actually got the best of both, right? I don't need to necessarily think about low-level details, but I can still get all the benefits that the underlying system provides. Right. So for example, if I have a client that wants to deposit $100 into his bank account and he wants to query what the balance is, right? If I run under an eventually consistent system, purely eventually consistent system, the deposit might go to one replica, the get balance might appear on another replica, as we've talked about, and this would be bad, right? On the other hand, if I had an implementation that said, whenever you do a deposit, whenever you do a write, any read that follows that write in that session better witness that write, we would get a completely different structure, right? In this case, when I have a deposit that goes to one replica with a balance of 100, the get balance that might go to a different replica that hasn't seen that would stop, would block until that until that operation is actually propagated, right? And now we're okay, right? We'll actually get to see the right value, right? So our goal is to try to figure out how to do that. So for a particular application with a set of operations associated with it, right, we're going to try to figure out a way of relating the semantics of that method, deposit, withdraw, tweet, bid, so forth and so on, to a particular consistency level. And we want to prove that that consistency level will not violate those invariants. Okay. We've turned the question of reasoning about consistency into a question on semantics, right? There's a semantic structure associated with consistency, and we want to propagate that out into the language itself. Right. So the goal is, how can we do this automatically? Can we actually do this automatically? Because if we could, then we're not asking a whole lot from the programmer. Right? So here's our idea. So the programmer has to tell us what their requirements are, right? And the store, the underlying data store, is going to tell our system what it can do, right? These are the things that it's going to be allowed to do. And we want to have a language, a framework, a formalism that allows us to express either of these, right? We'd like to use the same formalism if we could. And we think of this as a spec, right? So there's a specification that the programmer gives us on their requirements. There's a specification that the store gives us on on what it can do. And once we do that, we'll build an algorithm that will automatically map, right? So we have this system that we've built in Haskell called Quillia that does exactly this, right? So the way that it works is you give me a Haskell program equipped with the ability to express replication in various forms, right? So it's a mirror of, we allow programmers to write replicated data types, not in the CRDT style, but in the style that we talked about in our operational semantics. Right? We compile the code using ordinary Haskell, but on the side, we take these specifications that we'll allow the programmer to write, and we'll try to construct a solution for these specs with respect to what the store provides. And that particular solution defines the weakest guarantees that the store must give me in order for this particular spec to hold. And then we run this on an off-the-shelf data store. So our system basically, what our system basically does is it builds its own little specialized runtime for every data type that guarantees that no violation of the invariants that we want can actually take place. Right? Okay, so let's just go through a really simple example, and then we'll probably have to close. So suppose that I want to build a bank account. So my my bank account is going to have three methods on it: deposit, withdraw, and get balance, right? And our invariant is that the balance always has to be greater than or equal to 0. Right? So I'm going to have a set of operations on my bank account, right? Just as we talked about before. So the effects that I can have are deposit some value, withdraw some value, or just get a balance, right? These are the effects that I have. So what is an operation? So an operation says, give me a set of effects and an action, and I'm going to tell you what the result is, right? So if on some replica I've got some effects that are sitting there, and you want to do something, combine those effects against this action and produce a result, maybe. Right? So what does get balance do? So get balance says, if I run get balance on some replica, right, I'm going to look at all of the effects on that replica that were deposit actions, and I'm going to sum them up, and then I'm going to I'm going to subtract all the things that were withdraw actions, and the end result is the result. Right? Withdraw is similar, right? It's going to say, well, as long as I can do get balance on some replica, and the result is greater than 0, I'm going to allow it to continue. Otherwise, I'm not going to withdraw anything. And deposit is just going to add something to the effect. It's just going to record the fact that it's depositing some value. So what we've done, so replicated data type is nothing more than a regular data type, except that we've got this list of effects that we're going to keep around, right? And we're going to try to do interesting things with them. So the question is, how do we actually capture an invariant, right? How do we translate this notion of balance greater than 0 into something that's actionable, that we can actually do interesting things with? So what we're going to do is we're going to define a language of contracts, right? So we're going to write down a contract, except that this contract is going to be statically discharged by an underlying solver. And it's going to define the space of correct executions that we can have. Okay? So our contract language is essentially predicate logic. It's just going to be almost a direct transliteration of the operational semantics of the things that we manipulate in our operational semantics. That is, it's going to have operations. It's going to have ways of combining operations. It's going to have various kinds of relations, like visibility and session order and things like that. And so the job of the programmer now is to say, given that my interest is balance greater than 0, can I reason about balance greater than 0 in terms of actions like visibility and session order, right? And our claim is that's a lot easier to do than thinking about re-engineering an entire CRDT. And I'll just go through some examples of how this might actually take place. Right. So we have these relations, and then we can add new relations on top. We can add happens before relations and all sorts of other things, right? So this is essentially just first order logic with a bunch of constrained first order logic, a decidable fragment of first order logic with seeded with a collection of relations that define the way dependencies are structured with respect to one another. So here's a really simple example. I want balance greater than 0, right? And the observation is that in order for balance to be greater than 0, as we saw yesterday, the way that we can get into a situation where the balance can be less than 0 is if two withdraw operations take place that don't know about each other, right? This guy does withdraw 50, this guy does withdraw 70, and they don't know about one another. Both think that they're okay because there was originally 100 in the bank, and then they flow into a common point, and then we find that there's a negative balance. So our goal is to structure the definition of withdraw, or assert a contract on withdraw that says that any pair of withdraw operations that are executed must be totally ordered, and have the runtime system, have our underlying system enforce that. Right? So if I have a session where I do withdraw, and another session that also does a withdraw, and these two withdraw operations are manifested as effects, right, A and B, we would like to write the following contract. The contract that we want to write is, for any withdraw that you write, that you generate, right? If that withdraw happens to be on the same objects, right? So if I have two withdraw operations, A and B, and they're on the same object, right? It better be the case that either A sees B or B sees A on whichever replica, on whatever replica we execute, right? That's a spec, right? It's one-line spec that summarizes the intent of what we mean by withdraw action, right? So once we do that, right, we hand that off to our solver, and it says, yeah, okay, I know the way that we're going to solve this is by enforcing read my rights consistency, or by enforcing a particular strong consistency property on the underlying withdraw operation, say, right? Here's another example. If I have a deposit, yeah.
The visibility relation, you must hold on not just the executing replica, but all of the replica paths in your propagation, right?
Strongly consistent, right? I'm sorry, I just want to make sure that I didn't misspeak.
No, we said the same thing.
Okay. Right. So here's another example. So suppose I have a deposit of 100, right? And I want to relate the meaning of how this deposit relates to withdraws. So remember in our previous example, when we talked about yesterday, if I do a deposit, I want to make sure that withdraws that follow that sees that deposit. Otherwise, we may get into negative balances again. So let's assume that I, in fact, allow a withdraw to see a deposit. What happens now if that withdraw action goes to another replica? So I deposit 100, withdraw 50, and now I take that withdraw 50, which was successful, and I send it off to another replica. Is that allowed? Well, we have to be a bit careful, right? Because if I send that to a replica that has not seen the deposit, right, it doesn't know that there's $50 in the bank. It might think that there's actually negative 50, right? So what we need to enforce is that if I try to do a get balance operation, say, on an action that on a previous withdraw, that I better also see everything else that was causally dependent, that withdraw was causally dependent on. So if I'm going to do get balance and get balance sees withdraw, it better also see the deposit. Otherwise, it's just going to get a goofy answer, right? So we can write this down, right? We can write this contract as follows. If I have a deposit effect and a withdraw effect, and the deposit effect is visible to the withdraw effect, and the withdraw effect is visible to me, I'm a get balance operation, I better make sure that the deposit is also visible. This is the definition of causal consistency, right? This is a causally consistent operation. And so, in this way, we can write down all sorts of consistency protocols. Now, I talked about consistency from the perspective of the client, but we can also express these same contracts from the store level, from what the data store provides. So the data store says, oh yeah, I can do certain things as well. I can give you certain guarantees as well. I can give you eventual consistency. I can give you causal consistency. I can give you strong consistency. And I can express what I mean by that in terms of these same kinds of relations, these same kinds of formula, right? So this is very neat, right? Because we've got the same language for expressing constraints on consistency in two different universes, right? So as long as the constraints provided by the store implies the invariance that the client requires, we're happy, right? So we're going to try to solve that particular formula, right? So in doing this, right, what we discover is that as far as the invariant of balance greater than 0 is concerned, it doesn't matter that I don't need to put in any constraints on deposits. If I had a positive balance before, the fact that I don't see a deposit now isn't going to cause that balance to become negative. So I can run that in an EC way. If I have a withdraw operation, I want to make sure that this withdraw is ordered with respect to every other withdraw operation and every other operation that exists. So I'm going to make that strongly consistent, because if I don't, it's conceivable that I'll get a negative balance. And get balance has to be causally consistent with respect to all other operations that it's seen, that occur in its session, right? So if I don't do that, then I might see some withdraw but not another deposit, and that would be bad. So we can now consider this kind of mapping. Okay. Let me see how much time I've got. 10 minutes. Okay. Right. So very briefly, I'll talk about two other notions. One is, can we generalize this to transactions? So far, I've just talked about single operations. Can I actually do the same kind of game, play the same kind of game over arbitrary transactions? And why are transactions interesting? Because unlike a replicated data type, where we've got one instance of the state, right? In a transaction, I've got multiple objects, and I want to relate all of these objects collectively together, right? So we need to enrich our contract language with additional relations that allow us to think about transactions. Okay, and so we've got some cute, very simple mechanisms there as well. So, for example, here's a really simple instance. Suppose that I've got a transaction where Alice wishes to withdraw 100 from a checking account and deposit 100 into a savings account. So now I've got two objects, a checking account object and a savings account object. So Alice's transaction may take place on replica 1, and it might end up propagating to other replicas, but it has to propagate in situ. It can't just sort of be done piecemeal. Bob's running something which is not transactional, right? So he might see he might see a withdrawal from one checking account, but have something go to somewhere else. Bad things happen, right? So we can do the same kinds of, in order to sort of enforce constraints and properties on transactions, we get to write similar contracts. So for example, if I want to make sure that the total balance that I see in an account that includes checking and savings is always greater than 0, say, and it's never going to become negative, I might write a contract that says the following. If you give me an operation, an effect, which is either a deposit or withdraw, and another effect, which is either deposit or withdraw, and I'm trying to do a get balance on that, let's assume that I have two transactions. Transaction 1, which has operations A and B. Transaction 2, which has operations C and D, right? If I witness the effect of A in transaction 2, right? That's that line on the top. Then I better also witness the effect of B when I look at D. What is this actually telling me? It basically says, if you see something from this other committed transaction, you better see everything else in that committed transaction. This is the definition of atomicity, right? So we can express the notion of what an atomic action means in the context of a transaction as a conjunction over these visibility relations, as in terms of conjunctions and implications over visibility relations. Okay, right. So let me go through this. So there's a whole bunch of other degrees of actions that we can perform. There's one last thing that I would like to very briefly talk about, which is how do I implement any of this stuff, right? So I've given you things in terms of just these sort of logics. How do I actually implement this in practice? So let me very briefly go through this and talk about this idea called bolt-on consistency. So I have these contracts. I write them down, but they don't mean anything until I can actually enforce the runtime system. I can statically check what the dependencies are, that your runtime system better give me causal consistency in order to do this. But how do I know that the runtime system can actually do that, right? In fact, it's unlikely that it's going to do that because these kinds of off-the-shelf systems like Cassandra aren't designed for this. So what we've done is we've essentially added a shim layer, a very small runtime that sits on top of a data store that is guaranteed, that knows about these contracts, right? That implements the characteristics that we want, that implements visibility and same object relations. So basically, the idea is that we represent, we propagate these contracts down, and we sort of manifest them in the runtime. And there's sort of two actions that are worthwhile talking about. So the runtime system has two jobs. It's got to know when to perform an operation, and it's got to know what effects to make visible to that operation, right? Those are the two characteristics that visibility and session order and all these other relations capture. So how do I do that? So I'm going to sort of build a dependency relation. I have these dependency relations in my contracts, and I'm going to sort of feed them down to the runtime system. And I'm going to classify all of these contracts into one of two forms. Something called an LB contract, which is a lower bound contract. And what is it? And what this contract says is, if I have some dependencies that I need to have happen, that I need to have held before I can run, make sure that those dependencies exist. Don't let the operation continue until those dependencies are satisfied. So, for example, if I've got a client with two operations, O1 and O2, right? And I run operation 1 on replica 2, and it generates some effect, right? And I run operation 2 on some other replica, right? Generates some effect. This would be bad if there was a contract that required session order relations between O1 and O2. So what do? The runtime system records that information, and when it sees operation O1 running on replica 1, and it sees that operation O2 is going to go to replica 2, and that O1, Ada 1 is not available, it essentially stalls that operation, right? This doesn't block the client. The client can continue, right? It's something that happens only on the replica side. And eventually, Ada 1 will show up on replica 1, and then we'll allow the operation to continue. Right? So that's the notion of lower bound. These are the sort of minimal guarantees that must be provided. But there's another idea, right? There's the dual notion, right? Which is an upper bound, which is maybe I have too much information that's available. And I have more than I want, but not enough. Not enough to make everything okay. So I've seen some effects, but not all of the effects. And so I want to get rid of those effects that I've seen thus far. So here's an example. Again, suppose I have two operations, O1 and O2. And O1 comes up in replica 1, right? And O2 also shows up in replica 1, right? This looks okay so far. Eventually, I'm going to send one of these effects to replica 2. I'm going to send one of these effects to replica 1, right? So Ada 2 has shown up in replica 1. Observe that Ada 2 really depends on Ada 1, right? That was the order in which things happened. So if I have another client that performs an operation, and it wants to effect this operation, should it see Ada 2 or not? The answer is no, right? It should only see Ada 2 if Ada 1 shows up. So the way that we can resolve this is by essentially blocking Ada 2 from O1. So these two notions of dependency tracking, by blocking things until things are visible, or by ignoring things, hiding things when we don't have enough information, is how we implement our runtime system. So with that, we're at the end. So with that, I'll close, and there's a whole bunch of more details about the actual performance of this system that I don't have time to go into. But surprisingly, it works very well, and it outperforms the state of the art as far as we can tell, in terms of both latency and scalability and all sorts of other neat things, all in Haskell. So there you go. Any questions? Right, because we make no constraints on the order on how much information any replica can send to any other replica at any given instant, right? So in fact, it may not be that replica 2 may have tried to send something to replica 1, but maybe it went through a different path. Maybe it was too big and it's stalling. There's all sorts of issues that we have no control over. Yeah. Yeah, that's a reasonable question. So the challenge is twofold. So I'm not disputing that libraries are useful when they can when on certain occasions. But how would I write a library for a bank account? What does that even mean, right? I've got a data structure. It's an ad hoc data structure, right? It's something that is relevant for this particular application. And so using a set or using a list, a CRDT list, may be completely inappropriate for this particular application that I'm running under, because observe that a CRDT library only guarantees eventual consistency. It doesn't give me any way of dealing with things that are stronger when I need something that's stronger than that, right? It just says at some point everybody will see the same value. Maybe that's the wrong value relative to the application that I'm writing. So I think that there is an important need for both, right? When you can, and that's one thing. The second thing is, it's really hard to write these libraries. It's really, really hard, right? So over a period of a decade, of well over a decade, the set of CRDTs that we have can be counted on, probably one hand, right? It's just really, really tough. And at the end of the day, it's not easy to compose them, to build larger CRDTs from them. There's work that people have tried to do in that space, but it's still very much an open question. So in the meantime, right, what do we do? So, yep.
Can you go back to the slide where you classified things for the deposit, the withdrawal, and the get balance? I guess my question is when you classify operations into eventual consistency for the deposit and get, so the deposit you say runs in ECD. So that's with respect to the positive balance invariant.
Yes.
But that also is making the assumption, so generally it's making the assumption that the operations under ECD are commutative. Like you may have something that under eventual consistency, delivery ordering gives you different per replica results. However, that the divergence of results doesn't imply the invariant is non-existent.
That's a very valid point.
So I guess, so does this rely on the programmer classifying applications in the classifying code in the context language as commutative? Or specifically encoding that in the context language?
Right. So there's no requirement that there's no notion of commutativity, because we express commutativity in terms of the encoding of visibility relations, right? So vis A B or vis B C implies underneath that kind of.
Okay. Okay. So yeah, I remember you had that on a previous slide, which
Right.
I guess connects to the other question I had, which was on the visibility ordering. You said you wanted to observe deposits and withdrawals in this like kind of causal ordering. Um, I guess the more general question is, have you considered that? So I think there's two approaches. You can say I want to observe them in this order, or you could infer that you had some ordering based on program order by analyzing the program order. Because I think what programmers want to, I think it's very difficult for programmers to classify based on visibility degree, and so it's going to appear in order 1, 2, 3.
Yeah. Right. You're absolutely right. Stay tuned.
Okay.
Yeah.
All right.
Right. Thanks very much.